Hey, so this is Joe, and this is the second video of the 13th chapter of Stewart's Calculus, and we're going to be talking about vector-valued functions with calculus. So first we're going to talk about differentiating vector-valued functions. And differentiating that, since in the previous video we talked about taking the limit of a vector-valued function, and all you do is you take the limit, the same limit that's out here, you put them into all the components of the vector-valued function, you make t approach the same value for each of the components, and you're good. So you might be able to guess then, if that applies, since the derivative is just a different kind of limit, you may be able to guess that you take the derivative of a vector-valued function r, and all that corresponds to is the derivative of each of the components with respect to t. So that's not terribly complicated. However, one interesting thing about differentiating vector-valued functions are some of the properties. For example, the product rule applied to either the dot product or the cross product. So let's talk a little bit about sort of the properties of differentiating vector-valued functions. So if we're taking the derivative of the sum of two vector-valued functions, or for that matter the difference between two vector-valued functions, we have the same property as when we take the derivative of the sum of two regular functions, two single variable functions, and that is you just take the derivative of each vector valued function. Oh, there you go, the derivative of each vector valued function, and then add them. Not anything new. However, if we're taking the derivative of the dot product between two vector valued functions, you may think, maybe there's some sort of different property that holds here than the normal product rule. And really, it just ends up being the product rule, but applied instead of normal multiplication between two functions, it's the dot product. So we take the derivative of the first vector valued function to the dot product of the second one, and we leave the second one alone, and then add to that the first vector valued function being left alone, and then we dot product that with the derivative of the second vector valued function. So really it's just the dot product, but we replace a normal multiplication sign with the dot product, and it's between two vector valued functions. And we have basically the same thing with the cross product. If we take the derivative of the cross product between two vector valued functions, we take the derivative of the first vector valued function, cross it with the second vector valued function left alone, and then we add to that the first vector valued function left alone, and we cross it with the second vector valued function, but we take the derivative of it. And the chain rule also applies in the same way that it does with normal functions with vector valued functions. So those are kind of all the properties that we need to know about when it comes to differentiating vector valued functions. Now let's talk about integrating vector valued functions. And this also is not going to be anything surprising or terribly complicated. So when we're taking the definite integral of a vector valued function, so that means that it's between two limits of t, we integrate with respect to t, the parameter, and we have our limits, and then that's going to equal just the integral with the same limits of each of the components of that vector valued function. So nothing too surprising and not very complicated. However, what if we take the indefinite integral, so that means there are no limits, of a vector valued function with respect to t? Well, if you remember from single variable calculus, when we take the indefinite integral of any function, there's going to be a plus c at the end, some constant, because the derivative of any constant is 0, so you need to account for the fact that there could have been a constant at the end of the function that you had differentiated before we're integrating. So what about with a vector valued function? So what we're going to need to do is, it's easier to, instead of writing this out in bracket notation, to write it out as the sum of some coefficient times our basis vectors. So we're going to write this out as the definite integral of the x component with respect to t, and multiply that by our basis vector, the standard basis vector I. Then we add to that the integral of the indefinite integral of the y component with respect to t times our j vector, plus the integral of h of t with respect to t of our k vector, and then we can add on our constant vector. So basically a vector, this constant, instead of being a vector valued function, it's just going to be some vector with constant components, because if you take the derivative of a vector with constant components, you're taking the derivative of each component, and those components are going to all end up being 0. And a vector that terminates at point 0, 0, 0 is just the origin. That's not you can kind of ignore that. So when we integrate a vector valued function indefinitely, we need to account for the fact that there could be some constant vector added on to this other vector with this other vector valued function, that there could be some constant at the end, or some constant added to each component. And the constant that would be added to each component, because you could express it, instead of adding the c, you add a little plus a, a little plus b, and a little plus c to each of these components, and then that constant would be accounted in the coefficient. Or we could take out the a, b, c, factor that out, and make that its own constant c vector, and that's just a little bit of a cleaner way to express that. So generally, we're going to write out our indefinite integrals like this in standard basis vector notation instead of this bracket notation right here. So now, let's go and do a couple of practice problems with differentiation and integration of vector valued functions. Alright, so we're going to do number 25 on page 876 in your book, and the question asks us to find the tangent line to this vector valued function at point 1, 0, 1. So I'm already going to call that point our R0 in terms of our line notation, because that's the point that's going through the line that we know it's going to be going through. So, in the same way that when we find the tangent line to a 2D curve, we take the derivative of that curve, and then that will give us the slope of the tangent line. We need to find the derivative. Remember, when we find the line of a function, we have our r, and that's equal to x, y, z, all of our Cartesian variables, and that's equal to our r sub 0, a point through the line, plus t times a v, and that v is going to be parallel to the line that we're looking for. So that v is our slope of sorts, if we're going to be drawing a parallel between finding the tangent line of a vector valued function and finding the tangent line of a 2D function. So in the same way that we need to find the slope by taking the variable in a derivative in a 2D function, we need to find our v, our direction, the vector that'll determine the direction of our tangent line, by taking the derivative of our s function and figuring out what that vector will be at the point t when s is r sub 0. So first, we need to find out when what t will be when s is equal to r sub 0. So we need to figure out what the x component is going to be when t equals. So we set the x component to 1 to the x component of the r sub 0 function and figure out what t will be. So we have to ask, so we can move this e to the negative t over, and we'll get cosine of t is equal to e to the t. Now, when is cosine and e, when are they the same? Well, when t is 0, e is 1, and when t is 0, cosine is 1. So we can say, alright, they're equal when t is 0. And let's just test this out with the y component. So we'll set the y component of s equal to 0, e to the negative t times sine of t is equal to 0. Well, when t is 0, sine is going to be 0, so that looks good there. And let's just try it with the z component for good measure. E to the negative t is 1. Well, when is e to the something 1? When t is 0. So there we go. It looks like s of t is going to be equal to r sub 0 when t is 0. So now what we need to do to find the v vector for our tangent line of s at r sub 0 is take the derivative of s and plug in for t equals 0, and then we'll get our v vector, the vector that determines the direction of our tangent line. So we'll get s prime of t, and that'll be equal to, and we're going to need to apply our product rule here, so we're going to get a negative e to the negative t, and then we leave the cosine alone, times cosine t, plus, but there's going to be a negative because the derivative of cosine is negative sine, so it's going to be minus e to the negative t, we leave the e to the negative t alone, times sine t. Now on to our y component. Our y component, we also need to apply the product rule, so we take the derivative of e to the negative t, we're going to get negative e to the negative t, we leave the sine t alone, plus, and then now we take the derivative of sine, that's cosine, we leave the e to the negative t alone, cosine t, and then we take the derivative of e to the negative t for our z component, and that's negative e to the negative t. So this is our derivative right here, and we need to find the derivative at r sub 0, and we know we get r sub 0 when t is equal to 0. So we plug in a 0 for s prime of t, and that will give us a -1, a 1, and a -1. So this s prime of 0 is equal to our v. This is our quote-unquote slope, if we're drawing an analogy to a 2D function, for our tangent line. So now we have our v. So we have our r sub 0 and we have our v. Those are both the things we need to determine a line, to describe a line in 3 dimensions. So we have r, which is our 3 Cartesian variables, is going to be equal to our r sub 0, which is 1, 0, 1, plus t times our v. And our v is going to be equal to -1, 1, -1. And now we can express that in any of the 3 forms that I described a couple videos ago, but otherwise, that is our tangent line L, that's our tangent line that lies tangent to s of t, this vector valued function, at r sub 0. And yeah, so that is kind of the most complicated sort of problem that you're going to need to do with taking the calculus with vector valued functions. So, and integration, it's basically just testing your single variable integration skills. There's not too much we can do when it comes to integrating vector valued functions. So that's it for this video. I hope that was helpful, and definitely stay tuned for the rest of the chapter and the rest of the course. Thanks.